use this formula every time you have a point charge. So this is for a point charge. Something that looks like a point charge, it could be an atom, it could be a molecule, it could be a bunch of charges next to each other. So from outside, what looks like a point charge, if something looks like a point charge, this is the equation that I use. All right, before I give you guys a break within the next 10 minutes. Okay, so I want to show you how to use this. I'm going to give you guys a few cases. All right, this is a really simple enough concept, except if you're not paying attention, it's really easy to get confused. Let's try to figure out the net electric field due to two charges on a line, just like that. All right, so I'm going to get a positive charge. I'm going to place a positive charge right here. I'm also going to get a negative charge and place the negative charge right here. All right, along the x direction somewhere. And then I'm going to have a reference point, P. This is my reference point, P, point of reference. Okay, so I'm going to be interested in the net electric field at that point. So which means that you have to find the total electric field at that point. Positive charge is the emitter, so electric field due to the positive charge is going to be pointing to the right at that point. So this is the direction of the positive electric field due to the positive charge. All right, the negative charge is a receiver, so the electric field due to the negative charge is going to be pointing to the left. All right, so the positive charge is pointing to the right, the negative charge is electric field due to the negative charge is going to be pointing to the left. All right, so now let's take a look at the net electric field at point P. So sum up the electric fields. I'm going to put P here, so it's going to be a point P. So that's our reference point. Okay, so positive charge, electric field due to the positive charge, which is this, is pointing to the right, so this is going to be positive. Electric field due to the negative charge, which is right here, is going to be, it's pointing to the left, so this one is going to be negative. Yeah. All right, so the next step is just fill in the gaps. For our point charge, this is what we get to use. This is the formula. All right, so this is your positive charge, this is your negative charge. R for the positive charge is going to be this distance. This is for the positive charge. All right, so for the positive charge, we have to use this. And for the negative charge, we get to use the same formula. All right, so for the negative charge, the distance this time is going to be this distance. And then you just sum them up. Okay, I'm ignoring the details. I'm just showing you how to set up these problems. We will do a problem though shortly. All right, so KQ. All right, let's make this Q1. Let's make this Q2. They don't have to have the same value. All right, Q1 and Q2. All right, so the only thing that they will have in common is K is going to be common to both of them, so I'm going to factor that out. So it's Q1, radial distance for the positive charge, Q2 divided by the radial distance squared for the negative charge. Okay, so this is a quick, fast example that I came up with. All right, so let's play this game one more time. This time, I'm not going to do the math. Let's just focus on the setup. Most of you guys usually get confused about this section. All right, so how do you know which direction this electric field is going due to a positive charge? And why is it that the electric field points in the opposite direction due to a negative charge? All right, so before we do one more example, guys, remember, positive charge is the emitter, right? It's going to emit the electric field. And you also remember that the negative charge is the receiver. Okay, so this little detail is what's confusing you. Positive charge is the emitter, so the electric field is going to be pointing in this direction due to the positive charge. Therefore, right at this point, it's going to point to the right. Got it? And negative charge is a receiver, so which means that the electric field is going to be pointing towards the negative charge. Hence the reason why the electric field is pointing towards the negative charge. Got it? All right, so that's the visual that you need to have. All right, so let's do one more quick example.
Right in the middle.
Okay, go back. All right, yes.
If you were to point in the middle, would it both point to the right then?
Okay, very good. Absolutely it would. Okay, so that would be a good example to look at. So let's do that. That's a couple of the concepts that I want to discuss. That's one of them. All right, so what would happen if you were to look at the electric field, total electric field right in the middle? All right, so let's place a reference point right here. Okay, and let's use that. Okay, so electric field due to a positive charge is going to point in this direction. And electric field due to a negative charge is also going to point in the same direction, right? Okay, so I think we kind of got disconnected. Okay, I got the. All right, I got disconnected here somehow. I. All right, guys, let's quickly go over the derivation for the charge disk. Okay, the stuff that I'm doing right now, that's from the University of Physics Optimized. I can't believe it just got disconnected. All right, so let's move forward. Okay, now this one is going to be important. I want you to just enjoy the complexity of the math. So we're going to be interested in the strength of the electric field due to your charge disk. All right, so this is going to be our charge disk. We're going to be interested in the strength of the electric field at point P. Okay, so the charge is going to be distributed onto the surface area. So we're going to just grab a small portion of it. This is known as the differential charge element, so a small portion. And we are going to be interested in the strength of the electric field at a radial distance from that net charge. And then we will locate this amount of charge, the small amount of charge that we are looking at, the differential charge, with respect to the center of our geometry. So this is going to locate the charge for us. This is going to be r prime. This is r. Don't get them confused. R prime is a displacement vector that's going to locate the charge for you. Okay, so z is going to be the vertical distance. Capital R is the radius of the disk. All right, so this amount of charge is going to cause an electric field in that direction, along the radial direction. Okay, so we will get to use the generic equation for the electric field due to a point charge. And notice that you're just summing up all the point charges along that direction. And then you're looking at the contribution of the point charges to the electric field. And because the net charge is distributed over an area, so there's going to be a charge uniform surface charge density. So net charge is going to get expressed in terms of the uniform charge density. Once again, using the same ideas. Okay, if you're looking at the contribution of the charges on the surface area, it's going to give you some kind of, it's going to give you a region which is going to look like a cone, and the radial components will cancel out. So the only component that's going to survive is the z component. All right, so the idea is the same as before. So the question is, now you got a differential area here, so how do you express the differential area before you set up your interval? Area for a circle is going to be pi r squared. If you express it in terms of differential area, you have to differentiate both sides. When you do that, you guys should have learned this in Calc 2. So the area is going to be expressed in terms of the differential of r dr. So it gives you a vector, so what gets differentiated is r, so you're looking at only r prime in this case. All right, so r, you're looking at all the charges that go from 0. R prime is what you're looking at. R prime is going to go from 0 to capital R. So you're looking at the net charge within that area. So you do a little bit of calculus, which I'm skipping. Normally, I don't expect you guys to spend a lot of time doing calculus. Either you look it up or use some kind of calculus calculator. All right, so K is going to get expressed in terms of epsilon naught. Okay, so at this point, the only thing I'm really interested in the results. Okay, so I'm cleaning everything up. I'm doing the cancellations. So this is the final equation. We're not going to use this final equation as is. We're going to look at the implications of this equation. There are two cases that we're going to look at. Case number one, what is the strength of the electric field right at the surface? Okay, guys, when z is 0, what do you get out of this? All right, so z is going to be 0 here, z is going to be 0 here. So what do you end up getting? So in the limit, the z goes to 0. This entire portion goes to 0. This is the equation that you're left with. Okay, so what does that mean? Which means that the strength of the electric field right at the surface only depends on the charge density divided by 2 times that constant. That's it. Which means that the strength of the electric field right at the surface is going to be constant. All right, so for the charge insulating disk, like it could be rubber, it could be plastic, the strength of the electric field at the surface is going to be constant. Case number 2, make R extremely large, which means that you're dealing with an infinitely long disk, charge disk. If the charge is infinitely big, what would happen to the strength of the electric field? It's still going to remain constant. it's going to remain constant. This is for a charged insulating material. For a charged desk, if it's a metal desk, you get rid of 2. For a charged desk, the strength of the electric field is also going to remain constant. All right, so if the strength of the electric field remains constant for a charged desk, let's try to use this. Here's the sort of stuff that's going to kick your asses, guys. Here's what the math gives you. It says, here's the charge density. All right. For a charge desk, it's going to look like this. Question. Why is the strength of the electric field inside a charge desk constant? How do you justify something like that? So this is what you need to know. Guys, when you're taking the test, electroscope looks like this. This is known as the gold leaf electroscope. So gold leaves would be right at the bottom. All right, is this positive charge, negative charge, or is it neutral? It is neutral, right? It's got equal number of positive and negative charges. All right, so bring a negative charge rod near, what happens? It becomes polarized. All right, so the positive charges will get pulled to the top, the negative charges will be repelled to the bottom. Notice that the leaves will repel each other. Okay, so one of the questions that you will have to answer is, given the fact that these leaves are repelling each other because they have the like charges, why is it that there's an angle here? Why is it that this thing is not flat? How do you explain that? All right, so moving forward. Okay, so bring a negative charge rod near, the top is going to be positive charge. Leaves will be negatively charged, so leaves will repel. If you bring a positively charged rod near, opposite is going to happen. All right, so what happens if there's contact? Notice that if there's contact, negative charges will be actually, they will move, they will get transferred to the metal itself, so the metal is going to become negatively charged. So you can charge something up through contact. So transferring charges, charging by contact, this is what we're talking about. So now this becomes negative charge. All right, so if you bring a negatively charged rod nearby, once again, negative charges will be repelled, so the leaves will get pushed up. That's what's going to happen. Okay, so you guys kind of got that. All right, now let's talk about charging by induction. How does that happen? You got this metal sphere. It's on an insulated stand, so the charges will not leak out. That's what it means. You got your negatively charged rod. If you bring the negatively charged rod near, what happens to the metal sphere itself? It becomes polarized at this point. All right, so one side is going to be positively charged, the opposite side is going to become negatively charged. Okay, a couple of things that can happen here. And this is something that you need to kind of pay attention to, because if you don't, you will get confused on the test. All right, so one thing that I could do is I can actually ground the opposite end. Grounding simply means that you get a wire and then you connect it to the ground. That's what it means. All right, so you provided a pathway for the charges to leak out. All right, so when you bring a negative charge rod near, what happens is going to keep the positive charges right at the surface while it's repelling the negative charges into the ground. So what would happen if you were to get rid of the grounding wire while you still keep the negative charge rod nearby? So if you were to get rid of the grounding wire, what's going to happen? It'll be positive charge, right? Okay, so this is called charging by induction. So which means that you polarize one surface and then you ground the opposing surface. So the like charges will leak out, and then you get rid of the grounding wire, and then you will notice